Hi, everyone, and welcome to our last talk before the closing reception. I'm Blake Covarrubias, Senior Product Manager for Consul here at HashiCorp. So in this talk, I'm going to be giving you a technical deep dive of a new feature in Consul called cluster peering. Now, you may have heard a little bit about this in Armand's keynote earlier today, or in Paul Banks' presentation on the Consul roadmap. So before diving in, I want to give you a little bit of background on the current state of multi-cluster connectivity in Consul. So currently, Consul supports federating multiple data centers together to provide centralized management of ACL tokens and policies across many Consul clusters using a feature called WAN federation. And WAN federation supports cross-data center service discovery, which is useful for connecting services across different data centers. This works by forwarding the remote service lookups over the WAN using cross-data center RPC requests. When using Consul for Service Mesh, Federation provides the ability to establish secure service-to-service communication across clusters using mesh gateways. And now, this enables applications to use the same zero-trust security model to establish cluster communication as they use within the local data center. Cross-data center traffic can also make use of more advanced routing configurations like application failover and layer 7 traffic routing. Consul replicates all of these configurations and policies to all federated clusters so that your policies are consistent across the federation. Now, this model has met the needs of our community for quite some time, especially when it was common for organizations to run single large compute clusters that were administered by a central platform team. However, we increasingly see that organizations are deploying separate clusters that belong to different teams within the organization. And these clusters are typically operated by those teams, not the single platform team. And so in this model, it kind of became clear to us in talking to our customers and our community that WAN federation might not be the best fit for organizations that are deploying infrastructure like this. All right. Good to go? OK. So like one particular example would be with regard to cluster management. So many organizations, they don't have a single administrator that's managing all of their compute clusters. If they do, then that person's kind of feeling the pain of managing infrastructure at scale. I'm cracking? OK. Use this instead? OK. Hopefully that's better. So typically, organizations will have a platform team that's responsible for maintaining shared services across all of the different across the organization, and this team will provide services like metric collection, logging, and networking. And so in really large organizations, there may be multiple independent teams that are responsible for operating different cloud or infrastructure on different cloud or runtime environments. And these teams need the autonomy to be able to define local security keys, policies within their environment that are specific to their own domain, and even manage upgrade activities for their compute clusters distinct from other teams. And so in these types of environments, deploying Consul across these clusters and forcing teams to use to align to a single unified configuration and management model just doesn't make sense anymore. And so from a platform team's perspective, they're typically tasked, even in these types of environments, with facilitating network connectivity between these different environments. And in order to do that, they still require some degree of coordination across the different clusters in order to ensure that services can be successfully interconnected across these different compute environments. However, so from a connectivity standpoint, some of these independent teams within the organization, they may not need to connect to every other cluster within the org. They may only require or only need to connect to a smaller number of clusters. And so in Consul WAN Federation, it supports or uses a full mesh of connectivity between clusters by default. And so that model really doesn't make sense for these connectivity needs. And so we listened to the community, we heard this feedback, and in Console 1.13, we've introduced a new connectivity model to solve for these challenges called cluster peering. And so with cluster peering, this enables teams to connect services across clusters, but obviously has some key differences from the current WAN federation model. With cluster peering, services can be managed by different teams in different console data centers. And with using Console Enterprise, these teams can also leverage console admin partitions. Now, admin partitions saves the overhead of running servers for each team within your organization by using a shared multi-tenant control plane. And so again, this eliminates the need for each sub-team in your org to deploy their own console servers, allowing them to run less resources, but still get the benefit of running and using service mesh that's being operated by the shared platform team. Admin partitions also maintains each team's ability to be autonomous and define their own configurations and their own policies. And when you combine this with cluster peering, then these teams can still achieve service-to-service connectivity across partitions, whether those are in the same data center or even across different data centers and cloud environments. Okay, so in a second, I'm going to provide you a quick walkthrough of the cluster peering UX. But before I do that, I want to kind of cover some key terms. So the first is a peer. A peer is a cluster that exchanges service information with another cluster. And so if we use a telephone as a metaphor, if you and I are on a phone call together, we're peers. A dialing peer is the cluster that initiates a peering connection to another peer. And so if I called you on the telephone, then I'm the dialing peer. The accepting peer is a cluster that's receiving connections from other peers. And so if you answer my phone call, then you're the accepting peer. A peering token is what enables connecting to and authenticating peering sessions between peers. And so using the telephone analogy, you might say that a telephone number is the token. And then lastly, we have peering sessions. And so these are a bidirectional channel to exchange service information. As long as a session is up and running and the peering connection is healthy, then service information can be exchanged. If, for example, our peering connection was unhealthy, using, again, the telephone analogy, it might be because I don't have international calling. Okay, so don't worry if you missed any of those definitions. It's probably going to begin to make a little more sense as I actually demo the features and then go into a deep dive. So first, let's just explore the basic UX. So in this example, I have two clusters. US East 1, this is going to be my dialing cluster, and then AMS DC 1, and this is going to be the cluster that will receive the inbound connection from the other peer. So when setting up peering, the first thing you need to do is generate a peering token on the accepting cluster by using the console peering generate token command. You can assign a local name for the peering connection that identifies the peer we're going to be communicating with. In this example, we're using the dialing peer's name, which is US East 1. And then in the dialing cluster, in order to establish the peering, you'll need to use the token that was generated in that accepting cluster. And so we'll use the console peering establish command. We'll provide the token, as well as, again, a local name that identifies this peering session. In this case, AMS DC1. So once the peering connection is up and established, you'll need to advertise services that you want to make accessible across the connection. And you can do that by using an exported services configuration entry. In this config entry, you provide a list of consuming peers that you want to advertise a service to. Okay, let's take a look at how that actually looks from the console UI. So again, on our accepting cluster, we need to first generate a token. We'll do that by clicking Add Peering Connection, and then selecting the Generate Token tab, entering a peer name, and click Generating Token. Once that token is generated, we'll need to copy that token over to the other cluster so that we can initiate the peering connection. So in the other cluster, we'll follow, again, a similar process. We'll provide a name for the peer, import the token, and click Add Peer. And again, once peering is established, we'll be able to see a list of imported services right in the service listing, along with a peer name that identifies where that service came from. And we'll be able to monitor the health of each of the peers in the peering list. Now, this will show information like the status and the last heartbeat, which indicates when we last heard from that peer, and will also show information like the imported and exported services. Now, if for any reason the peering connection becomes unhealthy, then we'll see that status reflected here in the UI as failing. This could be because either there was a break in the connection, someone on the other end disabled the peering, or any other reason. And correspondingly, you'll see on each of the imported services the lack of status on those services, which indicates that these service entries might be stale in the catalog. Okay, so that was a high-level overview of kind of how the peering UX works and how cluster peering might help solve some real-world connectivity problems for organizations. But let's actually dive in a little bit deeper and see how this works under the hood. And so again, as I mentioned, in order to establish, establishing peering, this allows independent clusters or partitions to exchange service information. And you do that by creating peering sessions. So in order to use peering, your environment first must satisfy a couple of different networking prerequisites. The first is that the dialing cluster must be able to make outbound TCP requests on port 8300. The cluster receiving the peering connection has to be able to then correspondingly receive connections on TCP port 8300. And then both clusters must permit inbound and outbound service communication for the IP addresses either of the services or the gateways that are being advertised across the peering session. And so functionally, this means that your network needs to permit a communication model, something like this. Okay, so for this example, again, we want to establish peering between two console clusters that are deployed in different regions, US East 1 and AMS DC 1. And so in order to establish that peering, we'll do so by generating the token. Now in this example, we're doing this on Kubernetes using a peering acceptor custom resource. So we see the kind in this example is set to peering acceptor. We have a name, again, which defines the name for this local peer within the peering list. And then we're defining or specifying a secret where the Kubernetes secret where the token will be saved into. And so now this particular step is not necessary, but because this is kind of a technical talk, I want to give you some insight into what is actually stored into a token. If we were actually to decode this, you can see a couple of different parameters here. One is that the token contains the addresses of the remote peer where the dialer needs to connect to in order to establish peering. It also contains the name of the remote peer, so we know when we're connecting to it that we're connecting to the right endpoint. And it contains a peer ID. And this peer ID is used to, on the accepting cluster, to associate the incoming connection with the right peering session on the acceptor. And so next, after the token is generated, we have to export it to a file so we can provide it to the other cluster. And we'll just do that using kubectl get secret, save that to a file. And then the token needs to be transferred securely to the other cluster or the other cluster operator using some kind of out-of-band secure delivery method. This could be like encrypted email or any other thing, but again, it's handled out-of-band separate from console. Then that other cluster, the other cluster administrator will import that secret into their cluster, use it, and then they will need to create a peering dialer resource that references that secret in order to initiate that connection outbound to the accepting cluster. Once that dialer resource is created, then console will actually create an outbound gRPC connection over to the accepting cluster. The accepting cluster is going to receive that connection on TCP port 8300, and then it's going to authenticate the request using the information that was in the token. Assuming that information is valid, then the peering session is going to be established. Okay, so let's look at what's actually exchanged across the peering session. I mentioned that peering sessions exchange service information, but they also exchange other information. For service mesh, they exchange TLS information that's necessary for supporting encrypted cross-cluster service communication, and then they also communicate a heartbeat that's used to signal the health of the peering connection. If a cluster stops receiving a heartbeat, then it knows that this will be reflected in the console UI and APIs. Okay, so now that we have a peering session established between two clusters, let's take a look at service advertisement. So by advertising a service, this makes it discoverable to a remote peer. And as I was showing earlier, services are exported or advertised to peers using an exported services config entry. And so in this example, I've deployed a service in each of our example clusters. I have a front-end web service in AMS DC1, and that's configured to talk to a back-end API service in US East 1. And so in order to make the API service actually reachable across clusters, Consul must be configured to advertise that service over the peering connection. So we'll do that by creating an exported services config entry. We'll specify the name of the service that we want to export, in this case API, as well as the peers we want to export that to under the consumer list. So AMS DC1 in this example. Once that exported config entry is created, Consul is going to advertise the API service over the peering connection, and the receiving cluster is going to save this locally in its service catalog so that it can be resolved by other services that want to connect to this service over the connection. And so then if we query the service catalog from the AMS DC1 cluster for service named API that received across from US East 1 peer, we'll see that in the service catalog entry with a peer name identified in the service definition. And so this actually has a couple of important benefits from saving this information locally in the cluster. First is that it avoids the need for a cross data center RPC lookup in order to resolve services between data centers. And also it allows for services to continue to be resolved and connected to if for some reason the control plane communication between clusters, the peering connection between clusters is down, but say the data plane connection is still up and working. Okay, so now we have established peering between two clusters. We've advertised services to them. How do we actually connect to these services? So we'll need to actually configure now the web service to connect to the API using a couple of additional configuration. And so as it's probably apparent already, we know when a service is received from peers, it's now in the service catalog, and it can be looked up just like any other Consul service. When a service is received from a peer in the context of service discovery, those endpoints, those addresses that are propagated can be directly connected to. When you're using cluster peering in the context of service mesh, then you need to route your traffic through a sidecar proxy in order to communicate to that destination service. And so in order to make this API service accessible by web, we're first going to configure the web services proxy to route connections received on a specific local port over to the API service. And we'll do this by adding the connect service upstreams annotation to the web's deployment in Kubernetes. Now, this annotation specifies the name of the peered service that we want to expose and the local port that it should be made available on. And if we kind of zoom in on that a little bit, we can see the syntax of that. Pretty straightforward, that we have the name of the service we want to connect to, API, the peer that that service is available over, and the local port the proxy should expose it on. And so now, once this is set up, when the web application makes a connection to localhost port 1234, the proxy is going to first route that connection to its local mesh gateway, which in turn is going to route the connection to the remote cluster's mesh gateway. And then ultimately, that will route to the destination API service. So some details on actually connections between clusters. Keep in mind that these connections that are taking place between these clusters with cluster peering are happening between independent service meshes that are using separate PKI roots of trust. So for example, on one end, you could be using Vault. The other end, you could be using another CA, maybe something rooted in your corporate HSM. Cluster peering is taking care of exchanging the right information so that you can have trust between these different TLS domains, between clusters, and establish mutual TLS between services when using layer 4 connections. Or in the context of layer 7 connections, Consul acts a little bit differently. TLS connections are terminated at the edge, at the mesh gateway. And this is so that if you have configurations like layer 7 routing policies, things defined, that they can be used when within the destination cluster when routing to that destination service. Say, for example, if you have traffic splitting in place, you might want to split that traffic to version of API and another newer version of the API service. Okay, so now let's talk about service authorization. So earlier, I just showed how services can be made discoverable by exporting services using exported services config entry, and then how you can resolve them by looking them up in the service catalog. Now, when services are imported into a cluster, they can actually be looked up by any other service within that cluster. And so from an authorization standpoint, or say, for example, in a zero trust service mesh environment, typically traffic is denied by default. And you have to be very explicit on allowing which services can communicate to other services in the environment. And so you have to define a policy which permits that communication. And we do that with cluster peering using service intentions. Now, if this seems familiar, it's because it is. It's the exact same communication model that Consul uses for inter-data center communication, or sorry, authorization policies that it uses for inter-service communication today. And so again, going back to our example, in order to allow the web application to reach API, we'll create a service intention on US East 1 that authorizes inbound connections only from the web service in the AMS DC1 cluster. And we could see that by the new peer entry that's listed in the source intention config. Now, I'm not going to go into all the details of exactly how this works. I think I'm a little bit short on time to do that. But if you are interested in kind of what's happening here with regard to connection authorization, feel free to find me after and ask any questions that you have. Okay, so at some point, after you have service connectivity between peers, you may decide that you actually want to stop advertising a service to a specific peer. And you can do that by unexporting the service. And so when you unexport a service, it makes it undiscoverable from those peers. And you unexport a service by just simply removing it from the exported services entry, configuration entry. So again, going back to our example, we now have 2 services listed here. We just need to remove or delete this API service. Once that is saved into Consul, that'll issue an update across the peering connection to the remote peer, notifying it that that service is no longer valid, at which point it'll purge that from its service catalog. And then alternatively, at some point, you may decide you just want to completely sever peering with the remote cluster. When you remove a peer, that will stop advertising services to that cluster and also delete any imported services that it received from that cluster. Deleting a peering session is pretty straightforward. You can do that just by deleting the peer dialer resource on the dialing cluster, and then correspondingly deleting the acceptor resource on the accepting cluster. Okay, so that kind of concludes the high level or some walkthrough of peering or cluster peering and how it works kind of under the hood. Just to kind of summarize, we covered how to establish a peering session between clusters and what information is exchanged over that peering session. how to advertise services across the peering connection, and then how to connect to services across different peers. And lastly, we just reviewed how to remove service advertisements and peers. Okay, so what's next? Currently, Consul 1.13 is available as a tech preview. We are soon going to be adding support for managing these peering sessions using Terraform, as well as communicating to services using transparent proxy, so that you don't have to define the local port like I was showing earlier. You can actually just use a DNS hostname when connecting to that remote service. And then lastly, we'll be introducing support for storing these peering credentials in Vault. So they're no longer just in Kubernetes secrets. If you're using Vault, you can use that as a more secure store for those credentials. Consul 1.13 will be available as in GA towards the end of July. But if you'd like to learn more about cluster peering, you want to try it out and provide us with feedback, go ahead and check out the documentation and cluster peering tutorial over on consul.io.